Welcome to the beginning of our in-depth training series on IEEE Standard 1547 to 2018, where our goal is to connect technical standards to real-world operational resilience. I'm Reza Kandezi, and this module focuses specifically on Sections 1 and 4, laying the groundwork for how distributed energy resources, or DERs, should interconnect with electric power systems. But rather than just review these sections at face value, we're going to take a deeper approach, viewing them through the lens of fault ride-through. The ability of a DER to stay online and help stabilize the grid during electrical faults, such as voltage dips, frequency excursions, or transient events. Section 1 of the IEEE 1547 to 2018 standard might seem brief, but it contains three extremely important ideas that set the tone for everything else. The purpose. The standard is here to define minimum technical requirements for DER interconnection to the distribution system, but it goes far beyond wiring diagrams. It's about performance, stability, and system-wide reliability. The scope. It covers all DERs connected to radial primary or spot secondary distribution systems operating at 60 Hz and less than 1000 volts AC. The evolution. The 2018 update is transformational. It moves DERs from passive generators to active grid participants. From the fault ride-through standpoint, this shift is critical. In older versions of 1547, DERs were allowed, or even encouraged, to disconnect immediately at the first sign of a fault. But with increasing DER penetration, this approach creates instability. Imagine hundreds or thousands of DERs tripping offline simultaneously during a minor voltage sag. The result? Amplified grid collapse, load imbalance, and longer recovery. IEEE 1547 to 2018 now explicitly requires DERs to ride through most fault events, and Section 1 frames this as a systemic responsibility, not just a device feature. This section also introduces the reference point of applicability, or RPA. This is usually the point of common coupling, the point where a customer system meets the utility's grid. All requirements for voltage, frequency, power quality, and protection apply at this interface. That's a critical distinction. A DER might internally manage its behavior, but only its external performance at the PCC matters for compliance. So when we think of FRT, it's the DER's ability to maintain grid-compliant output at the PCC during abnormal system events that determines its contribution to reliability. Section 4 is where we leave the conceptual domain and enter the technical foundation of DR grid interaction. It is the most comprehensive section in the standard and directly supports every facet of fault ride-through capability. Let's walk through each subsection in detail. Clause 4.1, Voltage and Frequency Ride-Through Boundaries. This clause defines the normal operating voltage range, typically 88 to 110% of nominal, and frequency range, 59.3 to 60.5 Hz, at which DERs must remain connected. But more importantly, it sets the stage for when a DER must not disconnect during abnormal, but still tolerable, grid events. In other words, when voltage dips to 90% for a few cycles, or frequency sags to 59.5 Hz, the DER must stay online and support recovery. This is the core definition of fault ride-through. Clause 4.2 Interconnection System Design. The DER interconnection system must be built to withstand grid-side disturbances. During a fault, inrush currents, electromagnetic interference, and steep transients are all likely. The design must include thermal and surge protection, redundant controls, and robust filtering to survive these events without spurious trips. From the FRT perspective, this clause translates to physical resilience. The DER must be built to endure faults. Clause 4.3 Isolation Mechanisms. Each DER must include a visible, lockable means of disconnect, allowing utility personnel to safely isolate it. While this is a manual safety requirement, it also interacts with automated FRT logic. For example, the DER's software should not initiate disconnects based on minor disturbances. It should distinguish between transients to ride through and real faults to trip safely. Clause 4.4 Prevention of unintentional energization. One of the most critical risks during restoration from faults is a DER backfeeding a de-energized grid. This can endanger line workers and damage equipment. DERs must monitor line voltage and confirm the grid is alive before reconnecting. This clause ensures that DERs only re-energize when grid conditions are clearly stable, helping transition safely from FRT to normal operation. Clause 4.5 Reconnection Protocols. Once a DER trips due to severe voltage or frequency excursions, it cannot instantly rejoin the grid. IEEE 1547 mandates a minimum 5-minute reconnection delay, or longer, based on utility protocols. This allows grid voltage and frequency to settle, and prevents the chaos of hundreds of DERs coming online simultaneously. From the FRT lens, the DER must wait, monitor, and synchronize before reconnecting, preventing cascading failures. Clause 4.6 Synchronization and phase matching. Before re-energization, the DER must synchronize with grid voltage, phase angle, and frequency. This requirement is especially vital for inverter-based DERs, which can energize loads independently. During FRT recovery, improper synchronization can cause circulating currents, voltage step jumps, or even hardware failure in adjacent devices. Clause 4.7 Withstand and immunity performance. This clause ensures DER systems are immune to electromagnetic surges, radio frequency interference, and abrupt voltage swings. Faults often introduce steep dV/dt and dI/dt profiles, especially when protection devices operate. DERs must tolerate these without resetting, desynchronizing, or failing their ride-through response. Clause 4.8 Grounding coordination. Proper grounding is key to ensuring safe and reliable DER operation. In the context of FRT, a grounded DER helps ensure accurate fault detection and contributes to system stability during asymmetrical faults like single line-to-ground events. Clause 4.9 Data logging and event records. DERs must store key measurements and event data, including trip times, fault detection thresholds, and ride-through metrics. Post-fault analysis by utilities depends on this data to validate whether DERs met FRT obligations or contributed to instability. Clause 4.10 Local interoperability interfaces. Even without wide-area communication infrastructure, DERs must provide local access, via USB, serial port, or Ethernet, to read and adjust settings. This allows field engineers to verify FRT parameters like voltage trip points, ramp rates, and reconnection logic. Clause 4.11 Surge immunity and protection. Faults frequently create voltage surges, whether from capacitor switching, transformer energization, or lightning-induced transients. This clause ensures DERs comply with ANSI C62.41 surge, withstand categories, preventing failures during grid disturbances. Sections 1 and 4 together define the foundation of IEEE 1547 to 2018. They establish the why and the how behind interconnection, and make clear that DERs must remain connected, durable, and grid-friendly during electrical faults. If DERs can't survive and respond to faults, they can't be part of a modern, resilient grid. That's why FRT isn't an add-on. It's baked into the very architecture of this standard. In our next video, we'll explore sections 5 and 6, where DERs go from just surviving faults to actively supporting the grid during them. That means injecting VARs, modulating power, and operating like true grid assets in real time. Stay tuned. Let's continue training on IEEE 1547 to 2018. In this segment, we focus on sections 5 and 6, where the standard introduces the active roles DERs must play in supporting the grid through dynamic control, especially under abnormal voltage and frequency conditions. This is where fault ride-through becomes not just a matter of staying online, but of contributing intelligently, proportionally, and dynamically to system stability during faults. Section 5 addresses voltage regulation, reactive power capabilities, and active power control strategies. Let's look at how each clause connects to real-world fault ride-through behavior. Clause 5.1 Reactive power capability. DERs must be capable of absorbing or injecting reactive power when operating above 5% of their nameplate active power. Why does this matter in an FRT context? Because during faults, especially voltage sags, the grid often lacks sufficient reactive power. Voltage support becomes a localized, fast-acting need. DERs are expected to behave like miniature VR compensators. IEEE 1547 mandates that DERs meet a minimum dynamic power factor range, typically plus or minus 0.9. Though some configurations require tighter limits, such as plus or minus 0.85. This ensures that DERs can push VRs into the grid during undervoltage events, helping raise voltage at the faulted feeder and stabilize adjacent load buses. Clause 5.2, Voltage Regulation Modes. The standard introduces 4 reactive and voltage control modes, which can be selected or coordinated depending on grid needs. Constant Power Factor Mode. The DER maintains a fixed relationship between real and reactive power. In FRT conditions, this mode is the least helpful since it lacks dynamic voltage response. Volt-VAR mode. The DER modulates reactive power output in response to terminal voltage changes. This is one of the most important modes for fault ride-through because it enables real-time voltage support during grid disturbances. Watt-VAR mode. Reactive output changes based on active power, useful during partial loading or curtailment. Volt-Watt mode. The DER actively reduces active power when overvoltage conditions are detected. This helps prevent additional energy from being injected when the grid cannot absorb it, essential during overvoltage conditions following load drops or fault clearing. Each of these modes is configurable, and IEEE 1547 encourages area EPS operators to define appropriate mode settings, including deadbands, slopes, and time delays. Clause 5.3, Prioritization and Conflict Resolution. Sometimes DERs receive multiple control requests. Voltage regulation, frequency control, and protection activation. IEEE 1547 resolves these potential conflicts with a prioritization logic. Ride-through obligations always take precedence over power quality control. Voltage and frequency protection thresholds override curtailment. Communication-based requests are superseded by autonomous response when communication fails. This prioritization ensures that during FRT conditions, DERs focus first on staying connected and supporting voltage or frequency, even if it means temporarily sacrificing optimization or economic performance. Clause 5.4, Control Implementation and Point of Application. Control actions must be applied at the reference point of applicability. That means volt-VAR response should be evaluated at the PCCC, not just the inverter terminals. Response time is another key FRT parameter. Although the standard allows up to 10 seconds for full mode response, most FRT-relevant actions, like injecting VARs or throttling watts, need to occur within 500 milliseconds to be effective. Advanced inverters often target a sub-cycle response. Now we move into Section 6, the beating heart of fault ride-through requirements. This section directly defines how a DER must behave when the grid is not behaving normally. Clause 6.1, Voltage ride-through requirements. Voltage ride-through requirements are defined using performance curves based on voltage magnitude and duration. The key regions include mandatory operation region, the DER must remain connected. Permissive operation region, the DER may stay connected. Trip region, the DER must disconnect if limits are exceeded. For example, a Category 2 DER must ride through a 50% voltage sag for at least 0.16 seconds, and it must withstand 88% voltage for up to 20 seconds. The rationale is simple. If DERs disconnect too soon, they can destabilize the grid. DERs must also not inject zero power during a sag. In volt-VAR mode, they should be pushing reactive current to support the system during the event. Clause 6.2. Frequency ride-through. Similar to voltage ride-through, frequency ride-through curves define acceptable high and low frequency thresholds and durations. Low frequency ride-through LFRT, stay connected down to 57 Hz for up to 300 seconds. High frequency ride-through HFRT, stay connected up to 62 Hz for at least 300 seconds. This ensures DERs contribute to inertia-like support, reducing the risk of wide area blackouts during frequency instability. Clause 6.3, Rokoff tolerance. Rate of change of frequency, or Rokoff, is a measure of how fast frequency shifts. IEEE 1547 allows utilities to specify Rokoff trip limits, commonly 1 to 3 Hz per second. DERs must stay online through such shifts to prevent false islanding or misoperation during cascading generator trips. In high DR penetration systems, FRT must be Rokoff immune. Clause 6.4, phase angle changes. Sudden shifts in voltage phase, such as during a transformer tap or fault recovery, can confuse inverters. The standard requires DERs to withstand small angle changes up to 20 degrees per second without disconnection. Clause 6.5, frequency droop and active power support. DERs must provide frequency droop control, modulating active power in proportion to frequency deviation. This is vital during fault events that cause underfrequency. By automatically increasing real power output, DERs provide synthetic inertia and slow the rate of frequency decay. Droop response parameters such as slope, percent per hertz, and deadbands are configurable, but the default must be present and active. Clause 6.6, return to service logic. After a fault is cleared, DERs should not reconnect immediately. IEEE 1547 mandates a reconnection delay of at least 5 minutes. Voltage and frequency must be stable for the entire delay duration. Ramp rates must be gradual to avoid shock loading the system. This ensures grid recovery remains orderly and avoids new instabilities due to bulk DER reconnection. Together, Sections 5 and 6 move the DER from passive observer to active participant in grid stability. DERs must ride through voltage and frequency faults. They must inject reactive power and adjust real power based on measured conditions. Their reconnection must be cautious, coordinated, and slow. Fault ride-through is no longer about just staying on, it's about contributing to the grid's survival and recovery in real time. Let's go to the next section in our advanced training on IEEE 1547-2018. In this session, we turn our attention to Sections 7 and 8, covering power quality and islanding protection. While these topics might seem separate from fault ride-through at first glance, they are tightly intertwined with ensuring that DERs support, not destabilize, the grid during and after faults. Section 7 addresses how DERs must behave during both steady state and dynamic conditions to maintain power quality. Let's examine each clause through the FRT lens. Clause 7.1. DC injection limitations. DC injection into an AC grid can lead to magnetic core saturation in transformers and excessive heating in capacitors. IEEE 1547 limits this to no more than 0.5% of the rated output current. During a fault event, especially for inverter-based DERs, there's a risk of unintended control behavior or rectifier response introducing DC components. A DER that successfully rides through a fault must still maintain AC waveform integrity. DC suppression is part of ensuring that the DER contributes to grid recovery, not degradation. Clause 7.2 Voltage fluctuations and flicker control. Voltage flicker is often associated with rapidly fluctuating reactive power or intermittent load behavior. DERs can cause flicker if their controls overreact to small voltage disturbances. In FRT scenarios, DERs are injecting reactive current in response to voltage sags. If this VR injection is unstable or overly aggressive, it can induce visible flicker at customer locations. Clause 7.2 ensures that during a fault, support actions don't cause new power quality issues. It's not just about riding through, it's about riding through cleanly. Clause 7.3. Harmonic current distortion. DERs must meet harmonic limits in accordance with IEEE 519 or equivalent standards. Harmonics are caused by power electronic switching, especially under nonlinear loads or control transients. During faults, inverter-based DERs may change switching frequency or enter nonlinear modulation modes. If harmonics are not tightly controlled, they can cause overheating, misoperation of sensitive loads, and resonance issues. So in FRT events, the DER's harmonic performance must remain stable, even under stress. This requires advanced filter design and high-fidelity control loops. Clause 7.4 Voltage range maintenance at PCC. The DER must manage voltage not just at the inverter terminals but at the point of common coupling. During a fault or upon clearing, voltage at the PCC can oscillate or collapse temporarily. A DER performing FRT must ensure that its contribution helps recover and stabilize PCC voltage. Clause 7.4 ensures accountability at the system interface, not just internal metrics. Clause 7.5, avoiding overvoltage contribution. Following fault clearance, especially when load is suddenly restored, DERs must avoid overshooting their voltage output. High post-fault voltage can occur when too many DERs inject power before the grid is ready. This clause mandates ramping and VR moderation to avoid creating a secondary overvoltage event after the initial fault ends. Section 8 addresses unintentional islanding, where a DER or group of DERs continue energizing a portion of the grid after disconnection from the main utility. Let's look at why this is critically important during fault ride-through. Clause 8.1, Unintentional Island Detection and Cessation of Energization. IEEE 1547-2018 mandates that DERs must cease to energize an unintended island within 2 seconds. During a grid fault, especially if a recloser operates, there's a risk that a DER could become isolated while still producing power. This creates safety hazards for line workers, and risks damage to equipment operating without proper voltage or frequency regulation. From an FRT angle, this creates a paradox. DERs must ride through faults but not ride through into an island. That's where advanced anti-islanding detection comes in, using active impedance shifting, frequency monitoring, and voltage asymmetry detection to differentiate between a grid fault and a true island. Clause 8.2, Trip behavior and coordination with protection devices. The DER must trip in coordination with utility protection schemes but not prematurely. During FRT conditions, a DER may experience a brief voltage or frequency sag. If it interprets this as islanding and trips too soon, it undercuts system stability. Clause 8.2 ensures the DER's anti-islanding detection is robust but delayed, so it waits long enough to confirm isolation before disengaging. Clause 8.3. Intentional islanding with utility approval. In specific cases, like microgrids, campus systems, or critical facilities, intentional islanding is permitted if pre-authorized. But even in these cases, DERs must behave predictably, stabilize frequency and voltage within defined limits, isolate safely, and reconnect only with utility coordination. This matters for FRT because intentional islands may rely on DERs to provide immediate post-fault support, acting like primary generation during system splits. Clause 8.4. Testing and validation of anti-islanding features. Utilities must be able to verify anti-islanding capability. DERs must expose settings and logs for review. In an FRT scenario, this is essential for post-event diagnostics. Did the DER stay online properly? Did it detect an island? Was its behavior coordinated? IEEE 1547.1 expands on how to test these features in lab and field conditions. Sections 7 and 8 ensure that DERs ride through faults cleanly and safely, maintain power quality through harmonics, voltage recovery and flicker suppression, avoid energizing islands and misinterpreting FRT conditions as disconnection events, log behavior and enable testing for compliance. These clauses reinforce that fault ride-through is not just about staying online, it's about staying online the right way. In our next session, we'll explore sections 9 and 10, looking at power quality and anti-islanding, two critical behaviors that ensure DERs do not introduce instability during or after fault conditions. Thanks for staying tuned. Let's continue building a resilient future, one inverter at a time. Clause 9.1, Technology-Neutral Functional Requirements. IEEE 1547-2018 makes it clear, whether a DER is a solar inverter, wind turbine, synchronous generator, or induction machine, it must meet the same interconnection performance criteria. This is vital in fault ride-through because it ensures consistent behavior across the network during grid events. Imagine a voltage sag occurring on a feeder with 3 DERs, each a different technology. If they don't respond uniformly, some injecting VRs, some tripping early, it creates coordination failure and potential collapse. Clause 9.1 requires that all DERs, regardless of internal workings, must deliver compliant performance at the point of common coupling. That means every DER must handle FRT ride-through curves, VR injection rules, and frequency support parameters identically, from the grid's point of view. Clause 9.2, test criteria per technology type. Different technologies may need different testing strategies to prove compliance. Synchronous machines might use field test simulations. Inverters may undergo software-in-the-loop or hardware-in-the-loop validation. The key takeaway is that DER behavior must be tested against the same FRT ride-through benchmarks. Test setups can vary, but outcomes must be equal. Clause 9.3, aggregated systems coordination. Modern DERs are often deployed in clusters. A solar farm with 50 string inverters is still one DER from the utility's perspective. That aggregation must respond as a single unit during faults. Section 9 mandates that aggregated systems coordinate fault ride-through behavior. No out-of-phase reconnections, no staggered tripping, no voltage fighting between subsystems. Every sub-DER must synchronize FRT compliance logic and recovery timing. Clause 9.4, compliance across system changes. If a DER is repowered, upgraded, or extended with battery storage, its FRT compliance must persist or be retested. DER behavior must be robust across lifecycle modifications. If Section 9 defined what DERs must do under FRT, Section 10 explains how they stay in sync with grid operators to deliver that behavior dynamically and securely. We're now entering the realm of digital interaction, data exchange, monitoring, remote control, all essential during real-time grid events. Clause 10.1, Interoperability Functions. IEEE 1547 defines 4 major data categories DERs must support: nameplate information ratings, model topology, configuration settings, FRT trip points, ride-through time windows, ramp rates, monitoring data, instantaneous voltage, frequency, status, output power, management functions, remote on-off, mode selection, parameter tuning. In the context of FRT, this means grid operators can observe DER performance in real time during faults. They can push configuration updates if local fault behavior needs adjustment. DERs can report whether they stayed online, injected VRs, or rode through correctly. Clause 10.2, Local Communication Interface. All DERs must include a local physical communication port, such as Ethernet, USB, RS-485, or wireless, accessible on-site. This port is critical for FRT tuning and diagnostics. Engineers can connect and verify voltage sag response logic. Utilities can download event logs post-fault. Firmware updates for FRT algorithm improvements can be applied. Clause 10.3, Communication Protocol Standards. IEEE 1547 supports multiple data protocols. IEEE 2030.5, SunSpec Modbus DNP3. The protocol must support secure, reliable, and timely data exchange, especially during critical fault events when milliseconds count. For example, a DER that rides through a frequency disturbance may need to receive a curtailment signal mid-event. That communication must occur without delay or packet loss. Clause 10.4, Cybersecurity Expectations. While IEEE 1547-2018 doesn't dictate specific cybersecurity practices, it mandates that DER vendors and integrators design with secure communication in mind, authenticated access to FRT settings, encrypted telemetry if external networks are used, audit trails for remote configuration changes. In fault situations, a compromised DER that receives spoofed control commands could trip, disrupt reconnection, or destabilize voltage. Secure interoperability prevents these threats. Clause 10.5, Communication Availability and Latency. DERs must respond to control inputs and issue performance reports within standard latency ranges. Typical telemetry update rates every 2 to 5 seconds. Configuration response within 30 seconds. Event logging near real-time on detection. This ensures grid operators can assess DER FRT compliance dynamically and intervene when necessary. Sections 9 and 10 ensure that DERs not only survive faults, but cooperate and communicate as part of an intelligent system. No matter what type of device you're deploying, it must meet the same grid-facing FRT criteria. Every DER must be able to share its behavior, receive updates, and provide diagnostics. Aggregated and modular systems must act in harmony, not chaos, during grid events. This is what turns DERs into grid allies, not just generators. In our final session, we'll examine Section 11, where all the rules come together in the form of testing, validation, and commissioning. If we've defined what FRT performance should be, Section 11 defines how we prove it. Stay tuned as we bring this technical journey to its conclusion.